Hello everyone. So today we are going to talk about cavity modes. Now we all know that within a laser there is apart from the lot of other things that are there, we have an active material and we also have a cavity. So the active material is placed between two reflectors. This is what we understand by a cavity. Now, just like the material we use as the gain medium, the active material, the material decides as to what wavelength we will have the gain in. So you have a typical response of the system. Similarly, the cavity parameters will also decide the modes that this cavity can sustain. So with all these informations together, it decides as to at what wavelengths the laser will laze. So it is important to know how a cavity behaves in such a system. So we go back to a very common system, which is Fabry-Perot cavity resonator rather. Now we might have come across you might have come across this in other places as well. It is nothing but two parallel reflectors, and we have so the way we want to do is what are the modes that are sustained by this cavity. So we need to mark some. So we have an incident beam which comes at an angle theta, and as you see that it gets transmitted. So let's say the transmittance of the electric field is given by small t. So if E naught is the incident electric field, then the transmitted part of the field is T E naught or E naught t. And then of course we have an identical reflector here, so the part that goes out on this end is E naught t square. But of course we have the reflected components as well. Let's say the reflection fraction of reflection of the electric field is given by small r, so then this part would be small r E naught, and here it would be small r t E naught, and this again comes on this side, so it would be r square, sorry, not r square, it should be transmittance, so it should be r t square E naught, and this part would be r square t E naught, and this would be r square t square E naught, and so on. We can keep on naming them. Okay, so this is one part of it, like how the intensity is changing per like internal reflection. So it reflects and some part gets transmitted, and as we go from one ray to the next adjacent ray, we see that we pick up a factor of r square. Fine, but there is also the phase factor. Of course there is a path difference between these two, and so there should be some like these are coherent beams, so there should be some interference. So whether it will be interfering constructively, destructively, they all depend on the parameters, rest of the parameters here. So what let's say the distance between the two reflectors is d, and so what should be the path difference? If you look at it, we have air everywhere, so it doesn't the only difference we have between these two rays are, if you draw a perpendicular line here, then if you see that this region is same as this, and this part of the beam is also common for both the rays. So if you consider these consecutive rays, the only difference between these two rays arise from this path length and this path length. So the second beam has this extra part there. And how do we name them? Let's say we call this length as A and this length as B. So the path difference between consecutive rays is equal to A plus B, and then it's just a geometry. The geometry consists of the angle theta and the distance, separation distance d, and one can easily find out that what is A is nothing but d by cos theta, and B is equal to A cos 2 theta. As you see here, this angle would be 2 theta. So if that's the case, then A plus B, that is the path difference, is given by, you can do the maths, it comes out to be 2D cos theta. So this is the path difference between two consecutive beams, the physical path difference. So when we talk of interference, we need to consider phase. So the phase difference between the consecutive rays is nothing but your wave vector into the delta z, or delta d rather, I should write it in terms of, I don't know, delta r may be the distance, but r we have something else, so let's just write it down as z, okay? And this is this delta z, so this is equal to your delta z. So if that is the case, then k 2d cos theta is what you have as your phase difference, which we may name it as phi. So if this is the phase difference, we keep it as of now between the consecutive beams. Now let's just figure out what about the magnitude of the field here. So the magnitude, we have already marked out the what are the values. So this is E0 t square, this will be E0 t square r square, and so on. So the final transmitted field, electric field, is given by E0 t square plus, it's a series, E0 t square r square, and of course reflection, and then there is this I phi that we have decided, this is the path difference between the consecutive ones, plus we will have E0 t square r square, sorry, r 4, another 2r will be there, I 2 phi plus dot dot dot. It's a series, and this we can write as E0 t square sum over sum m equal to 0 to infinity r to the power twice m e to the power I m phi. This series, and this further simplifies to E0 t square by 1 minus r square I phi. And this is still the electric field, but what we normally measure is the intensity. So the intensity I is nothing but your mod E0 square and t to the power 4 by mod 1 minus r square e to the power I phi. Now you have to understand that the small r that we say, the electric field reflected part, actually picks up a phase due to reflection, and that reflection, so r actually can be written as mod r e to the power I some phi r, some phase shift because of the reflection. So eventually when we write the expression for I, let's call it transmittance, so IT is E naught square is I naught, which is the incident intensity, T4 by 1 minus mod r square exponential. So here we make it by 2 just for the sake of convenience, and then this r square will give a phi r, so it will be I phi plus phi r mod square. This turns out to be, if we name phi plus phi r as some capital phi, this is the total phase change, then IT is I0 capital T square, where T is the transmittance as we call it, 1 minus r to the power I capital phi mod square. Okay, where T is T square and R is mod R square. So this is what we have substituted. So this is one intermediate form of transmittance that we get here. Now we just want to figure out what this denominator is. So if you just expand it, this comes out to be 1 minus r. R is real here, capital R is real because we have taken away the imaginary part, the phase term separately, and in that phi r term, so there is nothing, it's a real term, and this will be r exponential minus I phi, right? This is what we have to write here. So if you solve this out, break this up and solve, this comes out to be something like 1 minus r whole square plus 4r sine square phi by 2. So this goes in the denominator. And so if you just substitute this here and do the needful, you'll get to something much more simple. And the standard way of representing this equation is actually I is equal to I naught t square 1 minus r whole square 1 by 1 plus f prime sine square phi by 2, where f prime is nothing but all the reflectivity terms are in here, whole square. Now one has to also say that let's say there is no absorption in the system. For no absorption at the reflectors or any other losses, transmittance plus reflectance should be 1. If that is the case, this term becomes equal to 1. And so what we have finally is IT by I naught. So the ratio of the transmitted to the incident beam is 1 by 1 plus f prime sine square phi by 2. Okay. And so if we plot this function, you can see that there is a sine term here. So the sine term can be the IT becomes minimum when sine term becomes 1 or minus 1, and IT becomes maximum when this term goes to 0 and it becomes equal to I naught. So if I would have plotted this function, this IT, so if this is IT by I naught and this axis is capital phi by 2, if this is what we plot, when phi by 2 is 0, then this has a, when this phi by 2 is 0, sine 0 is 0, so you have IT equal to I naught, so this is 1. And then we have, for every this function phi by 2 equal to n pi, so pi, 2 pi and so on, it will always pick up a maxima which is 1, and in between where you have the phi by 2 is of the order of the odd multiples of pi by 2, it will become 1, and then this value of IT drops, so it should be something like this. So this is how the cavity modes will look like. So as you see, the top part is 1 and the lower part, this value is given by when the sine function becomes 1, and this is 1 by 1 plus f prime. So how deep, or the minima, the value of the minima depends on f prime, which in turn depends on the reflectivity. Now remember, the f prime was given by 4r by 1 minus r whole square. So for large values of r, this value becomes very small. So more higher, stronger the reflectivity, the dip is very strong. So you have like really nearly dark bands here. So these modes are not supported by the cavity at all. and that depends on f prime. Fine. So what one can just point out once again from this is that we have maximas. For maxima we need phi by 2 should be n pi, or phi should be 2n pi, and for minima, all the minima we have, you have to have phi by 2 is odd multiples, so 2n plus 1 some factor of pi by 2 in this form. Okay, or basically phi should be odd multiples, so 2n plus 1 pi. So these are the two position criterias, and from here what one can find is the separation between these peaks, like modes rather. So each of these bumps that we have, each of them are called modes of the cavity. Or cavity modes. Fine. So what one can try out, which I will not do, it is your assignment, is that find the FWHM of the modes. Okay, find this out, because you should be able to do this. You may need to take one approximation, a hint. Say take phi to be very small. If that is the case, you can approximate sine phi by 2 to be phi by 2. If you use that, you get an easy functional form, and what actually you will land up with is your FWHM comes out to be 2, basically FWHM comes out to be 4 by square root f prime. This is an assignment. Please work it out and see that this is what you arrive at. So you see, so long we have given like f prime, because of course there's something we will use as f. So let's get to that. So what we define f, we call something called a finesse. Now you have to remember one thing. So let's say I have a simple thing, that I have modes. Okay, I have modes. There are two parameters to this. One is how broad these modes are, so what is your FWHM, and the other one is how well separated they are. Okay, so some delta phi. So I may have broad modes, but they may be still far off from one another, and so they are well separated. So these two parameters define how distinct your modes will look like, right? So I can have very thin modes, very small FWHM, but they may be very close by. So then also it's not a good thing. So if you want well separated modes, you want them separated as well as they should be narrow. So these two parameters actually define the finesse of the cavity, which is defined as del capital phi. So how well separated the modes are. So this is basically separation of the modes. We want them more separated, so finesse, which we call as capital F, is proportional to the separation. Higher the separation, higher is the finesse. And we want less FWHM. We want them to be very narrow. So practically, if finesse is very high, these modes will be very distinct from one another. They will be narrow and well separated. So if we plug things in, you can also find out. So it will be something like the separation of the modes is 2 pi, and the finesse is, as I described, the FWHM is 4 by square root f prime, and this actually comes out to be pi square root r. If you substitute the value of f prime, this is what is called the thinness of the cavity. And see, it all depends on the reflectivity of the material, of the reflectors. Transmittance doesn't come in the sense, because T and R are related. T plus R is equal to 1. So practically how strong your reflectance is will define the thinness of the cavity. So this was when when the two reflectors are identical, but one can even generalize it. Let's say R1 is the reflectivity of the first and the second reflector. So let's say these are the reflectivities of the two reflectors. So they are not equal, let's say. So you can actually start off that way, or just we can see. So in that case, what we do is we replace R with square root R1 R2. That's how you do it. And so in that case, the thinness comes out to be F is equal to pi R1 R2. It was already a square root, so it will be 1/4, and 1 minus square root R1 R2. This is the general form of thinness in a cavity formed by two reflectors having reflectivity R1 and R2. Okay, so and we now have the idea of the modes. The next lecture will be we will now plug in and see what are the wavelengths and how we incorporate the material refractive index within a laser cavity, and also what is basically the gain bandwidth and the cavity modes together, how they play a role. Okay, thank you for today's lecture. Thank you.